Welcome to the 7th lecture in our course on high performance computing. In the previous few lectures we had learned in some detail a RISC instruction set, which we will use in examples in the rest of the course. And to start off one of the examples, I thought I would just remind you a little bit about something that we saw in the first or second lecture of the course relating to how a C program gets converted into a form that can be executed on the hardware. So you'll recall that this was done by a program translator. The example that we used was the program translator, the GNU C compiler. And the idea was that you typed your C program into a file. In this case, the file is called program.c. And what GCC does is it takes your program as input and generates as output an equivalent program in the machine language. And the default name of the equivalent program is a.out. Let's just back up a little bit. You'll recall that GCC does this. I had mentioned that there are a number of steps in this translation process. The C program, program.c, goes through CPP, CC1, AS, and LD before a.out is generated. And we had seen what LD does. LD was the linkage editor which merges or joins multiple files of the kind of program.o or math.o into a single file. So it generates an executable file out of multiple object files, machine language files. Now, I had mentioned that between these steps of GCC, temporary files are used for the communication between these different stages of GCC. And this is going to be of interest to us because we may be able to look at and learn something from some of those temporary files. In particular, I am going to talk about the temporary file which is generated out of CC1. And in this particular example, this should not read hello.s but program.s. Since the name of our input file is program.c, here you would expect to see a file called program.s. Now, the thing to note here is that I'm talking about several different files. Program.c is the initial file that you created. Program.s, program.o are temporary files created during GCC's compilation task. A.out is the ultimate output file. The math library file exists on the computer system. It was generated and kept there. So of these different kinds of files, it would help us to understand a little bit about what these files are like. So I had pointed out last time that both program.c and program.s are what are called text files. Basically, they contain characters that you can read. You could actually open either of these files using a text editor, and you could modify them, read them or write them. So they are user-friendly files in that you can read them. Whereas program.o, a.out, and the math library file, math.o, are what are called object files, and they are in binary. They cannot be opened readily with a text editor and read or written. On the other hand, you could write a C program for the purpose of opening any one of these files and studying their structure. And in fact, I had suggested that you could do this for the a.out file, that you could write a C program which opens a.out as input and studies its structure. I had mentioned that each of these object files has a well-defined format. Okay, now the thing to note here is that this program.s file is a file which you can actually read. And it's a file which is generated during the compilation process by GCC. Now, let me just tell you a little bit more about the 4 steps in GCC. I've told you their names, CPP, CC1, AS, and LD. And I've told you a little bit about LD, the linkage editor. So I won't say anything more about that, but maybe a little bit about each of the others. First of all, the first stage in GCC, what GCC does is something called CPP, or the C preprocessor. And without knowing it, you are all probably quite familiar with what CPP does. Because all that CPP does is to pre-process the file by handling all of the lines in your C program file which start with the hash sign. Basically, or the count sign, as you may call it. So the count sign include, count sign define. These are really commands which the C preprocessor is going to handle. And as a result, the file which is outputted by CPP would not contain any of these files. You know, for example, that the count sign or the hash include directive. You could mention the name of a file as an argument to the count sign include. And you know that the result of this is that the contents of the file which you have mentioned will get included into your program. And that's one of the kinds of things that CPP does. Count sign define actually defines something called a macro. And the job of CPP in connection with macros is a little bit different. But in general, what CPP does is to handle all of the directives of the kind count sign include inside the file. And in essence, what CPP generates as output is just an expanded version of your C program. It's still a C program. You could, if you could look at it by opening it in a text editor, you'd find out it is in fact an ASCII file, a text file. You would find out that all the lines of your C program are there pretty much in the same form as what you had typed in. Okay, now this file, the file which is generated as output by CPP, is the input to CC1. And CC1 actually does some compilation. So it translates from C into something like the machine language. But as you would have noticed from the diagram which we had over here, what CC1 does is it takes the output from CPP and generates a file. But the file that it generates as output is a readable file, program.s, which means that it's not actually a machine language file. We would expect that a machine language file is going to contain machine instructions in binary, and would therefore it's unlikely that it would be readable. Therefore, the program.s file, in other words, the output generated by CC1, is not exactly a machine language file, but something else. What is it? It's what you would call an assembly language file. It's an equivalent. So what CC1 from this diagram we would imagine is generating is an equivalent of your C program in something called the assembly language. And it's available in a file called program.s, which you can actually open and study. Therefore, this is of interest to us. So what is this assembly language? Well, the assembly language is very similar to the machine language. The only difference is that it's readable. And in fact, when we look at an assembly language program, we will find the mnemonics or some things very similar to them that we had talked about when we refer to the MIPS1 machine language or the MIPS1 instruction set. So there may be certain things which are not MIPS instructions inside an assembly language program and require a little bit of translation, but those would be almost trivial translations. And in addition, the assembly language program may make use of labels rather than making use of the actual addresses of operands. So in some sense, the notation that we were using when we discussed the MIPS1 instruction set architecture was for the most part what you might call assembly language notation, because we too are using mnemonics, in other words, words for the various operations of the instructions, and we were using labels rather than actual addresses. So what happens to the assembly language program which is generated by CC1? It's still not in a form that can be executed on the hardware because it's not a machine language program. So it is the task of the next stage of the compiler, in other words AS or the assembler, to convert the assembly language program, program.s in our example, into an equivalent object file or machine language equivalent called program.o. And that's all that the assembler does. So we now have a much better picture of what's happening in GCC, and we understand that one of the critical points that we can access along the way is the assembly language program. If we could find a way to ask GCC to produce and let us see the assembly language program, then we could actually see a very low language equivalent of our program, of our input C program, low level in the sense that it is very similar to the machine language, but in a form that we should be able to understand. So let's just look at an example of this. So let's suppose that my C program file was a simple program of this kind. You'll notice that there are I'm including the standard I/O library, I'm including the math library, the header file for the standard I/O and math functions. In this particular case, this program is using one of the math functions, and it's also using something which is going to come from the standard I/O library, which is why these two include lines had to be there. So it's a very simple little program. I just draw your attention to the fact that this program declares and uses a floating point array of A of size 100, and that other than the function main, it doesn't have any other functions. So there's just the main program, the main function which executes. Right, so if this was the input program which I passed to GCC, and I found a way to ask GCC to generate program.s rather than producing program.o, the object file equivalent, or a.out, the executable equivalent, what would I see? That's the question we will ask next. So as I had indicated, we would expect that we would see an assembly language equivalent of our C program. In other words, mnemonics and labels and various other things, which is what the compiler had basically translated our C program into. So let me just show you parts of the program.s. I'm not going to show you the whole thing, and we won't try to understand the compilation process or all the lines inside the program.s file, the assembly language file, but I'll just highlight some of the interesting things to observe. So once again, let me just remind you to note this. Our input C program declares and uses a floating point array A of size 100, and it has a function called main. So when we look into the program.s, it's actually a fairly large file. I was unable to fit it onto one slide. In fact, it doesn't even fit on 3 or 4 slides. So I'm just going to show you the early parts of the program.s. We're actually not going to get into the interesting part very much. So you'll notice that in the first part of program.s, there are a number of lines, all of which start with a dot, and none of which looks in any way related to our program. I noticed the identifier A over here, which must be something to do with my array A. But other than that, there's not much of use over here. Now, all of the lines that we see on the screen here are actually what are called assembler directives. They are lines which have been created by CC1 for the purpose of asking the assembler to do something. And since we're not particularly interested in learning about how an assembler works, I'm just going to gloss over this and move on to the next foil, the next slide. So if I look at the second slide, this is the continuation of the program.s, contents of program.s. And here I noticed that there is a declaration A. There's A with a colon after it, which suggests that this has something to do with assigning an address to A. And the interesting thing that I note here is that there's a directive called dot space 400. Once again, it starts with a dot, so it's an assembly directive. But it's from the name, you would guess that this is a directive which is requesting some space to be allocated. And in this case, the number of bytes of space being requested is 400, which seems to be easy for us to understand, given that the A that we're referring to here must be the array A that we had declared in our program. It was an array A of size 100 floats. Now we know the size of each float is 4 bytes, and therefore we know that the size of this entire array A is the 400 bytes of space which is being allocated. Now it looks from this particular set of lines inside the assembly language that A is being assigned space, not on a stack, because if it was being assigned space on a stack, we would have seen some indication of that, and not dynamically, because this is a static allocation. This is in fact an example of static allocation. The array A is being statically allocated 400 bytes. Okay, so I go further down and I notice that there's another label, and this is the beginning of a label for the beginning of my main function, followed by a number of lines, all of which are assembler directives. So I won't, once again, I'll gloss over those and move on to the next slide. Okay, now in the next slide, I notice there are a number of lines which seem to be copied from my program. But what follows is of interest, because the lower half of this slide, the part of the lines which are now gradually turning into red, are for the most part some things that we can understand. We have seen some of these before. For example, we see that this is the MIPS1 LUI instruction, which we all know is the load upper immediate. I had mentioned that this is an important instruction because it can be used to load an address into a register. And that seems to be what is being done by the instructions that follow. But again, for the moment, we'll just forget about that. After this, there is an add immediate unsigned. And notice that there is a 16-bit immediate operand, which happens to be the value -16. There's an add unsigned, there's a load word. These are all things that we understand. There is one instruction, one mnemonic among the instructions over here that we have not seen before, and that is this SF instruction. Now, the instructions that we saw which start with an S were SB, SH, and SW. And these were the store instructions. SB was the store byte instruction, which could be used to store 8 bits from a register into memory. SH was the store half instruction, which could be used to store 16 bits, the least significant 16 bits of the operand register into memory. And SW was the store word instruction, which could be used to store 32 bits from a register into memory. Here we have something called SF. This is in fact a store instruction to be used in connection with floating point values. As I had mentioned, when our discussion of the MIPS instruction set covered only the integer instructions, but the MIPS instruction set does have capabilities for processing floating point values, and there are more instructions which I had not mentioned, and this is an example of one of them. This is an instruction which can be used to store a floating point value from a register into memory. Similarly, there would be instructions which can be used to add floats, multiply floats, etc. A family of floating point instructions. But this is what we now understand we would see if we looked at a file like program.s. In other words, an assembly language file, one of the temporary files that is generated by GCC in the process of compiling a C program into an executable file. And in the assembly language program, we see that there are instructions which we have heard about. And conceivably, we could think of modifying the assembly language program. For example, if I wanted to add or change some of these instructions, I could edit the assembly language program and experiment with that, and then pass it back to GCC for continued processing by the remaining steps of GCC. So that's something of interest which we may look into later. So we now understand that while the machine language that we saw is meant for the machine to execute, there is a slightly more human readable version of machine language called the assembly language, and that is the level at which we are going to use examples, and that could also be the level at which one could modify one's program if one was intent on doing so at a very low level. Okay, so much for GCC. We will now move back to trying to understand the MIPS1 instruction set by trying to write some simple examples. Okay, now the first, the predominant example which I am going to use, this is a dual purpose example. We're actually going to try to understand the various the sequence of operations that has to happen during a function call and return. Right. This is going to be useful to us. So we have a general idea of how function calls and returns operate, but we'll look in detail at various things which must happen as a part of function call and as a part of function return, and we'll do so in the MIPS1 assembly language. So therefore, it's a dual purpose example. Now, if you look at the example that I have here, the outer yellow box is some program, and I'm concentrating on only two functions of the program, the function A and the function B. You notice that both of these functions do not return a value, which is why they are void functions. Function A does not take parameters. Function B takes one integer parameter. Now, in this particular situation, if you look at function A, you'll notice that function A calls function B with one integer parameter. And inside function B, there is a return. So we know that generally the way that the function call operates is when there is execution in function A, when one reaches the function call, rather than just going in executing the function call, rather than just going on to the next instruction in A, control is transferred to function B. So we were going down in function A, executing the instructions of A one after the other, until we came to the function call, at which point control gets transferred. So this was the control transfer associated with the function call. After this, the instructions of B are executed until the return, at which point control gets transferred back to just after the function call inside A. So this is what we know about function calls. And let me just first of all introduce some terminology. Now we have two functions over here. There's the function in which the function call is present, and there is the function which is being called. So since there are two functions, we need some terminology to distinguish between them. And the point in function A where function B is called is what we call the function call. That is fairly clear. The function in which the function call is made is called the caller function. So in this particular example, the caller is A. And the function which is being called, I will refer to as the callee. So in this particular example, the callee is B. These are fairly standard terms, caller and callee. So the function call is present inside the body of the caller, and as a result of the function call, control is transferred from the caller to the callee. Now often in a function call, as in this example, there may be the need to pass parameters. So in this particular example, the value 5 is the value that has to be passed by A to B, inside the function b, the parameter is known by the name x. So in this particular situation, the value, the variable x inside the function b would be associated with the value 5 as a result of this function call. That's how a parameter is passed from function a, or from the caller, to function b or the callee. So this notion of passing parameters. Then we also know that in functions, for example, here function b has two local variables. So the local variables of function b are the local variables of function b in this particular example are called a and b. Not very good names, but in this example that's what we have. So in b, the body of the function gets executed, and then there is the return, which is the point during execution when the control is supposed to be transferred back to the caller. And the question of where should control be transferred back in the caller is that control is transferred back to the point immediately after the function call, which is what we will refer to as the return address. Now, in your experience with programming, you know that there are many different mechanisms for passing parameters. This particular kind of parameter passing that we have here is called parameter passing by value, since the value 5 gets passed and is locally within the function known by the name x. The value of x could change. That doesn't cause any change to the value 5, obviously, because 5 is a constant. And there are other mechanisms for parameter passing which would be a little different from what we will be talking about in this example, but you will be able to understand how to work out those details on your own, I think. So we will just try to understand how this particular function call would work. Okay. So we need to understand what are the various low-level operations which must happen in order to allow for what we just saw, this functionality, to happen when the program containing these two functions is executed. Right? So we will break this up into the various things that must be done as part of the call and the various things that must be done as part of the return. And we are going to try to work this out at a very low level, because we ultimately want to write MIPS instructions corresponding to each of the steps that we are going to put down here. Now, what's fairly obvious is that when the function call occurs, there is a need to transfer control to the start of the callee, right? To the start of the callee function. In other words, the function call happened in A, so there's a need to transfer control to the start of function B, or the callee. So that's one of the things that must happen as a part of function call. Similarly, as part of function return, it's fairly clear that one of the things that must happen is that control must be transferred back to the return address inside the caller. Right? So just to make sure you understand what I'm doing here, there are many steps which must be executed. So I'm going to list all of them one after the other. Right? Many different other steps are going to pop up here one after the other as we understand what the steps are. And one of the early steps in doing the function call is the need to transfer control to the start of the function. There may be one or two steps before that, which is why I've left a gap over here, and obviously several steps after that, which is why I've left gaps over here. Okay. So now we understand that as part of the function call, there is a need to transfer control to the start of the callee, and as part of function return, there's a need to transfer control back to the return address inside the caller. Now, one issue which this raises is the following. As part of function return, there is a need to transfer control back to the return address inside the caller. Now, this activity, in other words, the transfer of control, is going to be an instruction inside the callee, inside the function which was called. Remember that the function return is inside the callee, and therefore the instruction which does transfer of control back to the return address is going to be inside the callee. Now, inside the callee, unless I explicitly had remembered what the return address was, there would be no way for this transfer of control back to the return address to happen. Right? So unless at the time of the call we had remembered what the return address was, then at the time of the return it would not be possible to identify the return address. Therefore, going back to the point of call, we now realize that one of the important things that must happen at the point of call is that before we execute too much inside the callee, we have to remember the return address within the caller. That's important. All right, so to remember the return address, we have to use memory. So the question which we need to first figure out is, how and where do we remember the return address? We're going to concentrate on this step for a few minutes. How and where and do I remember the return address? Now there are many possibilities. One possibility is that I could remember the return address in a general purpose register. And in fact, for those of you who remember the jump and link instruction, will realize that the jump and link instruction remembers the return address for you inside register R31. We'll come to that shortly. Now the problem with thinking of remembering the return address in a general purpose register is that this may not actually be a safe solution, because there's no guarantee that the general purpose register in which I save the return address will survive with the value that I had saved there for long. Let me just give you a simple example. Let's suppose that I have a situation where there is a function called a, which is calling itself. In other words, a recursive function call. So a calls itself, and then a might call itself again. A recursive function call is a function. A recursive function is a function which calls itself. Right? So the situation here is that function a calls itself, and then inside so there's the first call to function a, there's the second call to function a, there's the third call to function a, one after the other. Now inside after the first call to function a, there's a need to remember the return address of that call, and I might save it in a general purpose register. But after the second call to function a, there's a need to remember the second return address. And if I have a single piece of code for the function, then it's going to use the same return address that I had used for the first saving. In other words, the same general purpose register will be used for that purpose. You could also see how this problem may arise if there are other sequences of, for example, if there's a nested function call, function A calls function B calls function C. Then if I'm using register R31 to remember all return addresses, then in transferring control from A to B, the return address inside A will be present in R31. But then inside function A, when I call function C, register R31 will be used to save the return address inside B, and I will therefore lose the return address inside A. Therefore, in general, just thinking that I can save return addresses inside a general purpose register is not going to work. We need something better. So this may not work because, well, this is another reason that this may not be a good idea. What I've written over here is this may not be a good idea because the callee might have been compiled to use that register for its variables. Let me just explain what this means. Now the idea here is that I'm suggesting that when function A calls function B, as part of the function call, in remembering the return address, I might remember the return address in register R6. In other words, R6 will contain the return address inside function A. Now you'll remember that function B is itself a piece of code which does execution of various instructions, and it's conceivable that functions A and B were compiled separately. In other words, I may have written function A in one file and compiled it. Function A may have been present in a file called 1.c. Function B may have been present in a file called 2.c. And I may have compiled 1.c and got a file called 1.o. And I may have later compiled 2.c and got 2.o. And then ultimately I may have linked these files together. That's what I mean by saying that the A and B may have been compiled separately. Now if this is the case, then when I compiled 1.c into 1.o, the compiler may have used many registers for many things. For example, the compiler in this example may be using R6 as the return address. Later on, when I compiled 2.c to 2.o, the compiler once again is using registers for various things, and there's no telling what it might have used R6 for. So this is another reason that just using a general purpose register to remember a return address might not be a good idea. So we have to look for alternatives. Just using a general purpose register is not a sound solution. Okay, now another possibility then is that I could remember the return address in a variable, in other words in a main memory location. Okay. So the simple idea here is that when function A calls function B, then associated with the return address of function A, I could have a memory location which I can refer to as A return. And when the function call happens, I'll remember the return address of function A inside that variable or that memory location. And this won't have the problem with separate compilation that I had talked about, but it will have the problem with the case of nested or recursive function calls that we had talked about prior to that. Therefore, just using a memory location to remember the return address may not be, again, an adequate solution for all situations. Therefore, we need something different. The next possibility that we'll talk about is, since I'm concerned about losing a return address if I use one register or one memory location, why don't I just try to remember return addresses on a stack? In other words, in main memory on a stack. The advantage of using a stack is I'm not using one memory location, I'm using any number of memory locations. If I have to remember 6 return addresses, I'll push them onto the stack one after the other. And therefore, this will not have a problem with recursive function calls or with nested function calls, and is in fact a reasonable solution for our current situation. Right? So, we are going to assume that this is what we will do. We will assume that when there is a function call, as part of the transfer of control to the caller, to the callee, the return address must be remembered, the return address inside the caller, and that will be done on a stack in main memory. Now, we've already seen that stack allocated variables, such as the local variables and parameters of a function, are going to be allocated space on a stack. So, we could just use the very same stack for remembering the return address. So, the stack that we talked about earlier, where stack allocation of space for variables is done, is going to be used not only to allocate space for local variables of a function and for parameters of a function, but also for remembering the return addresses of calls to functions. So, there is going to be a single stack which will serve all these purposes. With this, we have tackled the problem of transferring control to the function and back from the function to the caller, because we now know where to save the return address. Now, just to make sure we understand what a stack is, let me quickly recap what a stack is. So, when we talked about stack earlier, I had mentioned stack is a data structure, and when thinking about a stack, you think of a stack of books. In fact, that's where the name comes from. On this table, if I were to stack books, I would put one book, and then if I wanted to add another book to the stack, I would add it on top of the first book, and if I wanted to add a third book on the stack, I add it on top of the second book. Then if I wanted to remove a book from the stack, I would remove from the top, because if I try to remove lower books, I could either damage the books or hurt myself. So, the general property of the stack is that it's a data structure which has operations of putting something new on top of the stack or removing the topmost element from the stack. And these operations are usually called push for the insertion operation and pop for the deletion operation. So, both push and pop deal with the top of the stack. Therefore, in an implementation, and as I had mentioned last time, one thinks of the stack as being a last in, first out data structure, because it is the last thing that you put into the stack. In other words, the book which is on the top of the stack, which is the next thing that you will get when you pop from the stack. So, that's called a last in, first out data structure. Now, very clearly, since the focus of interest of the stack is the top of the stack, in implementing a stack, we will need to remember the memory location. The stack is going to be implemented in memory. As we said, it's going to grow depending on, as more and more elements get pushed onto the stack, it will grow in memory. But at any given point in time, we will need to keep track of which element is the current top of stack. And we will think of doing that using a variable or pointer called the stack pointer. So, the stack pointer is a variable which always contains the address of possibly the current top stack of the top element of the stack. And stack pointer is typically abbreviated as SP. Okay. Now, moving on, we will try to understand how we could implement a stack using the MIPS instructions. Since we are clearly going to need a stack to do the function call, our objective at this point is still to understand the function call and return mechanism completely, but there is this sub-problem of being able to implement a stack, because the stack is important for the implementation of the function call, because that's where the stack is where the local variables and the parameters are going to be stack allocated, and the stack is also where the return address is going to be remembered. So, since we are going to need a stack certainly for the implementation of function call and return, this aside will help us to understand how a stack could be implemented in the MIPS 1 language. Okay, now to make sure we understand the push and pop operations, let's suppose that I have a stack And currently the situation on the stack is that there is a value 3 on the bottom and a value -4 on the top. They happen to be there from previous operations on the stack. Therefore, the current stack top of stack pointer will point at the -4. And so if I were to, if there is a stack pointer, it currently points at the -4 element. At this point, if I was to push a new value onto the stack, how would this change the stack? The answer is the 47 would be an additional value on top of the stack, and the stack pointer, instead of pointing at -4, would now point at the 47. So this is what the stack would look like after a push 47. What would happen if I then did 2 pop operations? Remember, each of the pop operations is going to remove the topmost element from the stack. Therefore, if I do 2 pop operations, the first one would remove the 47 from the stack, and the second one would remove the -4 from the stack, leaving only the 3 on the stack, and the stack pointer would be pointing at the 3. So this is what the stack would look like after 2 pops. So with this we understand that to implement a stack, I must allocate space in memory, or I must have space in memory for the stack to grow. I must have something which will point at the topmost element in the stack, and whenever there is a need to push onto the stack, I have to store new values into memory and update the stack pointer. Whenever there is a need to pop something from the stack, I need to change the stack pointer. Right? So very clearly the operations are quite simple. We just have to see how to implement them in the MIPS language. We'll possibly come back to that shortly, but for the moment it's clear that the instructions which will be used to do these operations are going to be very, very simple. There may be, in order to push something onto the stack, if the current stack pointer is pointing here, if I wanted to push 47 onto the stack, I would have to use a store instruction, because to write anything into memory I need to use a store instruction. And in order to modify the stack pointer to point over here, I would have to use some kind of a add or multiply instruction. I'm sorry, some kind of an add or subtract instruction, depending on what the nature of the stack pointer is. In this particular example, it looks like the stack is growing into a lower memory address, and therefore I would have to subtract from the value of the stack pointer. If the address of this memory location was 100, the address of this memory location would have been 96 if the size of each stack element is 4 bytes. Which is why I said that in order to put the 47 into this location, I would have had to use a store word, because the stack is in memory. And in order to update the stack pointer, I may have had to use a subtract instruction or an add immediate instruction with an operand of -4, by which I could subtract 4 and get the 100 to point to 96. So the instructions dealing with implementation of the stack are going to be maybe a pair of instructions for a push and a pair of instructions for a pop. And for the push, it's going to be a store and an add immediate, and for the pop, it's going to be a load. In other words, copy a value from memory into a register, since I want the popped value to be available for some purpose. So the stack seems to be fairly easy to understand. So let's go back to the function call and return. This is where we were. We understood that as part of function call, I have to transfer control and remember return address on the stack. As part of function return, I have to transfer control to that return address. What else has to be done? Now we had seen that the function A, in calling the function B, passed a parameter. And the parameter in that particular example was the value 5. But in general, if parameters have to be passed, then there must be a mechanism by which the parameter which was known to the caller becomes known to the callee. And once again, one way to do this is actually to pass the parameters on the stack. There are other ways to do it, but let's just assume that this is how we are going to implement the function call. So how will we get past the value 5 from the caller to the callee? We'll do so by allocating space for the parameter on the stack and putting a 5 into that particular location on the stack as part of the function call, which is why I put pass parameters on the stack as something that must happen before I transfer control to the start of the function. Because once I transfer control to the start of the function, I'm in function B. Right? So this is the point at which I move from function A to function B. At this point, I'm in the caller. At this point, I'm in the callee. And I know the value of the parameter only when I'm in the caller. Therefore, the passing of the parameter must be done inside function A. And that is why it's the first thing that must be done in this sequence of steps. What are the other things that must be done? Now, as we know, before I actually start executing the body of the function which is being called, its local variables must have space allocated for them. Therefore, the last thing that I talk about doing as part of the function call is going to be to allocate space for the local variables of the function which is being called, for the function b. And as we had already agreed, that is going to be done on this same stack. Right, now, unfortunately, there are still many steps that seem to have to be filled up. So we seem to be about 2/3 of our way done with the function call and return, but it's not clear what remains to be done until we remember that, unlike our particular example where both function a and function b are void functions and do not have the need to pass return values, in general functions may have to pass return value. In other words, the function which is being called, the callee, may have to pass a value back to the function which called it. And that would have been the example in our case too if the function b had been declared as an integer function. Because if function b had been an integer function, then the situation may have been something like this. The return instruction which would have mentioned the value that has to be passed back to the function a. So in general, we have to be aware of how one can pass a return value from the function which was called back to the function which called it. And at this point, it should be fairly clear that one way to pass the return value would be for the function which is being called, the callee, to push the return value onto the stack so that after control is transferred back to the caller can just read the return value off the stack. So return values too can be communicated through the stack. Okay, now we are nearing the end of our sequence of steps because there is not a whole lot of white space left. But there seems to be some critical functionality that has been left out. And as it happens, this relates to the separate compilation issue which we had talked about. But I'll come back to that in a second. Now, in this sequence of steps that we have, you'll notice that a lot of things were getting pushed onto the stack. At this point, we haven't talked about removing anything from the stack. And therefore, passing parameters on the stack is pushing. Remembering the return address on the stack is pushing. Passing the return value is pushing. So all of local variables on the stack is pushing space onto the stack. Therefore, as a result of any one function call, a lot of space is going to get allocated on the stack. And unless we explicitly include the reclamation of that space inside our series of steps for what has to happen during a function call and return, the stack will just keep on growing indefinitely. Therefore, explicitly over here I have a step which says clean up the stack. In other words, pop all the different things which had been pushed onto the stack in connection with this function call, so that the stack is back to the situation that it was at the point of the call. Right? So the cleaning up of the stack is basically popping of the various things that had been pushed onto the stack as part of the implementation of the function call. All right, so we're almost there. Now there's only one or two more things that have to be done. And these, as I said, relate to the problem with separate compilation. Now, I had briefly alluded to this a little while back, but let me spell it out in more detail. Now, separate compilation is the idea that the program which you are compiling may generate a .o file as a result of the compilation, which has to be linked with other files, such as a math library. And in the compilation of program.c into program.o, it's possible that CC1 used some registers in order to, for frequently used variables, in order to speed up the execution of the functions inside that particular part of the program. So let's suppose, for example, that CC1 used general purpose registers R3 through R10 inside program.o for the frequently used variables of that function, of the functions inside program.o. Now, it is quite possible that these same registers are used by the functions inside math.o. We have no idea what registers are used by the functions inside math.o. Therefore, it's certainly possible that R3 through R10 were used inside the math library functions as well. So if that's the case, then whenever a function of mine inside program.c calls one of the math functions, the values which it assumes it had placed into the registers R3 through R10 would get overwritten by the use of those same registers inside the math function. Therefore, there is a problem here in that every time from within my program.c, a math function is called during the execution of the program. Values which were assumed would be available in R3 through R10 will disappear. They'll be overwritten by other values, and the program will not do what I thought it was going to do. Therefore, it is necessary, as part of the function call, that we save the values of those registers, in this particular example R3 through R10, as part of the function call, so that before control is transferred, in this case to the math library, the values of R3 through R10 have been saved, and then subsequently on return from the math library function back to the function which did the call, the values of R3 through R10 could be restored from wherever I had saved them. Therefore, the saving and restoring of registers whose values might be overwritten by the function which is being called is an essential part of the function call and return from our perspective. And that is in fact what remains to be put into this sequence of steps. As part of the function call, I need to save the values of registers. As part of the function call, which is up here, I need to save the values of registers which might be used, but which are being used in the function that is being called in the caller, so that they can be restored on return. So the registers are saved as part of function call, and they are restored as part of function return. And only those registers which are needed, in other words, the registers which contain values of frequently used variables, only those registers, as in our example, maybe only R3 through R10. It's not always necessary to save all the registers. The compiler knows exactly which registers it has been using for the frequently used variables and can therefore save only those. This, of course, raises one last question: where will the saving of these register values be done? And once again, the saving of the register values can be done on the stack. So the values can be saved onto the stack as part of function call, and they can be restored from the stack into the registers R3 to R10 by load instructions. So the saving is going to happen through store instructions, and the restoring is going to happen through load instructions back into the registers R3 through R10. So this is what happens in a simple function call. It's not as trivial as we may have thought. And all of this has to be implemented by the compiler or by the person who's writing the program if you're not writing the program in C. So if I was writing this program in assembly language or in machine language, I would have to do all these steps to achieve a function call. Or if my C program is being compiled by GCC, then it will have to include instructions in the machine language equivalent program which do all these steps. Okay, so let's just make sure we understand what I was referring to earlier about implementing a stack in memory. We understand what a stack is, and we understand that associated with the stack we must have a stack pointer. So since the stack pointer is going to be used very frequently as part of doing all the operations on the stack, I'm just going to assume that it's in the interest of the program to use a general purpose register as the stack pointer. And I will assume that I'm using R29 as the stack pointer, and that R29 will not be used for anything else. Right? And just for completeness, it is often the case that compilers will use, such as GCC, may use a particular register as the stack pointer. And for example, if you look at the assembly language program that we looked at, you'll notice that there is a reference to a register SP. The notation that they use in that particular assembly languages, they do not refer to the registers as R0 through R31, but they refer to them as, I think, %0 through %31. And one of the registers, therefore, is referred to as %SP. And that is, in fact, the assembly language way of referring to the register which is used as the stack pointer. And typically, I believe, R29 is the register which is used as the stack pointer. Right, so we need to use a register as the stack pointer to make the operation of the stack as fast as possible. Now, what could the stack pointer point at? Now, I had mentioned that the stack pointer should always contain the address in memory of the topmost element in the stack. But you could also choose to cause the stack pointer to point at the memory location of the next free location which will be used for the next push onto the stack. Either of these would be perfectly okay. There's no, just to point out that this is not the only way of implementing the stack in terms of the stack pointer. Now, the other decision that one may have to make about in terms of implementing a stack in memory in the MIPS assembly language or machine language is I may have to decide whether the stack grows up or down in memory. we talked about the stack having to grow. So if this is memory and the stack is currently up to this point, the question of whether it grows in this direction or grows in that direction is what we are talking about over here. In other words, does it grow into lower and lower memory addresses, or does it grow into higher and higher memory addresses? And typically when I use the word growing up in memory, I will be referring to growing into higher memory addresses. Therefore, the arrow moving in this direction is what we would refer to as growing up in memory. Just note that typically one would show the lowest memory address at the top and the highest memory address, say 1000 or whatever, at the bottom. And therefore, even though this arrow is pointing down, it is growing into higher and higher memory addresses, which is why I refer to it as growing up. The alternative is also possible, depending on how the allocation of the space of memory is being done by the system. All right, so just to run through a quick MIPS1 implementation. Let's assume that I have a situation where I'm growing. I want to write the instructions for pushing and popping elements onto a stack. And here I'm showing a region of memory which contains the stack. These are byte addresses. The addresses are shown in hex: 1234, 1235, 1236, 1237. So this is increasing memory addresses. Right, so I'm going to assume that the stack grows down in memory. In other words, it grows not in the direction of the arrow, but in this direction. It's growing into lower and lower memory addresses. What is what we mean by down? I'll also assume that R29 is being used as the stack pointer and that it points at the current top of stack element. All right, so let's assume that right now the stack looks like this. What does this mean? This means that the stack, there could be stack elements in higher and higher memory addresses, but the topmost element in the stack is at memory location 1237. Therefore, the stack pointer, which is in R29, currently contains the address hex 1237, because R29 points at the current top of stack element. How now do I implement push? Let's suppose that the particular stack which I am dealing with, the stack operations which I am dealing with, are to push a byte and to pop a byte out of the stack. How do I push a byte? In order to push a byte, I know that the new byte is going to occupy this memory location, right? And that in order to write something into that memory location, I could first of all decrement the stack pointer. How much do I decrement the stack pointer by? I need to decrement the stack pointer from 1237 to 1236, which is why I have this subtract instruction. Well, you could read this as we saw, there may not be a subtract instruction. So this might be add -1. Right? So just a minor change to this. Add immediate R29, R29 1, so -1. So what is this instruction doing? It is causing the stack pointer to get decremented by 1. And that is going to cause the stack pointer to now point at 1236. Now in order to push a byte onto the stack, I can use a store byte. Store byte into which memory location? Into the memory location with the displacement of 0 of the base register R29. In other words, into 1236 plus 0. Remember that this is the base displacement addressing mode, which is used in all load and store instructions. And the net effect is that whatever value I want to push, I'm assuming that value is currently available in some register, RS, some source register. It could be R6 or R7, whatever it happens to be. So the byte, the least significant byte from that register, will get written into the top of stack memory location. So these two instructions implement the push byte. How do I implement the pop byte? I could leave this as a simple example for you to work out, but it's clearly going to be the opposite in the sense that it's going to start with a load byte. In other words, read from memory that byte which is at memory location base address R29 plus offset displacement of 0. In other words, whatever the top of stack is currently pointing at, and read from that memory location into some register, the destination register. Again, this could be R5, whatever register I want the value to come into for subsequent computation. Subsequently, I need to update the stack pointer, which I do by incrementing it by 1. And the effect of that will be that the top of stack gets erased, and I can do the incrementing using add immediate R29, R29, 1. Now, before closing with this example, let me just talk about what I had previously over here. Previously, instead of using the add immediate instruction, I had used something called subtract immediate. But in talking about the MIPS instructions, I had explicitly said that is no need for a subtract immediate instruction, and therefore there would not be a subtract immediate instruction implemented in the MIPS-1 hardware, because whatever the subtract immediate instruction would do could have been done by an add immediate instruction. However, it is conceivable that in the assembly language, subtract immediate could be supported as an aid to the programmer. And all that the assembler has to do is that whenever it sees a subtract immediate, it can replace it by add immediate and then just take the negative of whatever the immediate value is. Right? So this is another kind of an example of what how an assembly language might differ from a machine language. Some additional simple instructions might be added, which might not actually be implemented inside the hardware, something like the subtract immediate, but which might be of value to the programmer in order to more easily understand and write programs in a style that is, let me say, more readable. So with this, we've understood the sequence of steps that must happen in a function call and return, and we've understood that a stack is a very important part of that sequence of steps. We've also seen how to implement a stack in memory using the MIPS-1 instructions. Thank you.